Derivative formulas continued. Now that we know the derivative formulas for polynomials, power functions, and trigonometric functions, we want to take a look at the remaining functions that we study in this course, and that includes exponential and logarithmic functions. For exponential functions, let's start with the example 3 to the x. So consider the function 3 to the x. If we want to approximate the derivative at 0, we need to look at the average rate of change really close to 0. So if we go ahead and pick negative 0.01 on the left and 0.01 on the right, we can use average rates of change to approximate the derivative at 0. So here, if we plug each of these values into our function 3 to the x, we get the following outputs. Now, I've elected to keep all of my decimal points, but you can keep them on your calculator or you can write them down. So here, we want to find the average rate of change on the left and the average rate of change on the right. So if we do change in y over change in x to the left, so 1 minus 0.98907400042 divided by 0 minus negative 0.01, I get 1.0986122. And when I do the same thing and I find the average rate of change on the right of 0, I get 1.104669194. Now, the reason I'm approximating my derivative this way, instead of using the definition of derivative, is that if I plugged in an x plus h, I wouldn't be able to manipulate the algebra to simplify it enough to get rid of the h. So instead, I'm using my average rates of change to approximate the derivative at this point. So looking at these two values, I'm pretty certain that my derivative here, f prime of 0, is pretty close to 1.1. It might be something like 1.09, but we can see that it has to be between 1.098 and 1.104. So I'm going to approximate it to be 1.1. Now, if we take a look at the picture of 3 to the x and a picture of the derivative, if we were to approximate the derivative at every value, what we get is the following. The original function, f of x, is in black, and the derivative function for every point is plotted in red. We approximated the derivative at 0 to be about 1.1. So you can see that that red function, the derivative function, crosses through at roughly 1.1. And if we approximate the derivative at the other values of x shown here, so from negative 4 all the way until 1, and you plot those, you get that red line. One thing that we notice here is that the derivative function is very close to the original function. They look very similar, only they're slightly off by a factor. So I suspect that the derivative function is going to be 3 to the x times some sort of constant, which will stretch the y values. Let's look at another picture to see if it helps illuminate anything. Similarly, if we were to graph f of x equals 2 to the x and the derivative estimated at several points, we get the following graph, where 2 to the x is going to be the graph that's in black, and the derivative at every point is the graph in red. Again, we see that it looks very similar in shape and curvature, and therefore we expect that the derivative of 2 to the x to be related to 2 to the x itself, maybe multiplied by some sort of constant. Looking at patterns of exponential functions, we're able to arrive at the following formula. The derivative of f of x equals a to the x, where a is some number, is going to be a to the x times the natural log of a. So that means that we're going to get the same exact function back times the natural log of the base. Let's look at a couple quick examples. So suppose that f of x equals 12 to the x. Exponential functions have a number in the base, and the exponent is where the variable is. According to this formula, I'm going to get the same function back, 12 to the x, but I'm going to multiply it by a constant, and that constant is the natural log of the base. And the base here is 12. So that'll work when the base is any number. Let's go ahead and see what happens because we're going to have a special case when we look at the function e to the x. So e to the x has a numerical base. E is approximately 2.71. And so when we take the derivative, we're going to get the same thing back, e to the x, times the natural log of the base. But if you remember from algebra, the natural log of e is 1. So that means that the derivative of e to the x is e to the x. That's a special case of this rule, and it's really helpful. We use e to the x a lot. So knowing that the derivative is the same as the original function is a really helpful little trick here. So now we're going to add that to our formula list that we had from before. So currently, our updated derivative formulas list looks like this. We know the derivative of a constant. We know the derivative of a linear function. We know the derivative of a polynomial or power function, sine, cosine, exponentials, and the special case of exponentials of e to the x. Let's do some examples now. Example 1. Use the formulas to find each of the following derivatives. So for the first one, we have 7 to the x. Our formula says when we have an exponential function, we're going to get the same thing back times the natural log of the base. So the derivative is 7 to the x times the natural log of 7. Our next function is e to the x. That was our special case we just talked about. And so the derivative of e to the x is e to the x. 1.2 to the x, again, is going to be an exponential function because we have a number raised to a variable. So we're going to get the same thing back, 1.2 to the x, times the natural log of the base, 1.2. Finally, we have pi to the x. Remember, pi is a number, and so we have a number raised to the x, which is an exponential. So our derivative is going to be the same thing back, times the natural log of the base. So we're almost done with all of the formulas we need to form what's called the basic derivatives. We have one more that we need to add to the list. So let's take a look at this last one.